Okay, so let us now have this hinge problem. So this is a prop beam supported by a fix and a roller at the end. So hinge is present at point B. We're going to draw the influence line diagram for letter A, reaction at A, letter B, reaction at D, and then moment 3 meters from A and the shear 3 meters from A. So I have already drafted here solution. So first, you're going to determine the ILD for reaction at A. So as you can see, the procedure is that when we have an internal hinge, you are going to separate that and then use equilibrium equations to solve for the unknown. So our concern for now is reaction at A. So of course, there will be distinct equation for the left of B and the right portion of B, because as one will abandon this portion, there will be no reaction at A. So just left of B, we can write summation moments at B. So we have this unit load times moment arm, that is 4 minus x, okay, and then plus 4 times RA is equal to 0. So by arranging the equation, solving for RA, we will be having 1 minus 1/4 of x. So this is the equation we are going to utilize for now in order to come up with the reaction at A, considering the left portion. And then considering the right portion, okay, RA is always equal to 0. Why? Because 1 already is no longer present on this segment AB. So if there is no loading, consistently RA will have no value, or that will be always equal to 0. And by the way, this equation is x applicable to a distance that is less than 4, or 4 minus, and this is a distance wherein we consider distance that is greater than 4, or 4 plus. Okay, so these are the two equations that will be used. So if we are going to tabulate this one, say we have x with its corresponding RA when x is equal to 0. So using this term will cancel, and RA will be equal to 1. Okay, so when x is 4 minus, okay, meaning it is within B, but it will not be greater than B. Okay, so when x is equal to 4, we substitute in here. 4 over 4 is 1. 1 minus 1 is 0. And if we have just right of B, RA will be equal to 0. That is why our influence line diagram will look like this. So from 1, it will have a 0 value at exactly 4, okay, and onwards. So it will have 0 value at that portion. So again, 1 starts to abandon just the beam, or AB, at a distance that is greater than 4. That is why RA here will be consistently equal to 0 from this point up to the end of your beam. Now, interestingly, RD is not directly related to RA, but RD is greatly dependent on the shear at B. Okay, so RA is related to shear at B, and then we can connect, or we can relate RD to RA through the shear at B. So we will be needing the ILD for RA this time. So as we can see, when your unit load is still on AB, okay, we can use this one, or just left of B. So this red portion is actually intended for the shear at B, which could relate to reaction at D. So here, the shear at B, we use this one. Actually, this came from summation forces vertical is equal to 0 using this left portion. Now, if we do that, we can say that RA plus VB will just be equal to 1. Now, if we solve for VB, we come up with this equation. So, we transpose RA, we have 1 minus RA. And then eventually, we can substitute the value of RA from this and then expand. And we will come up that shear at B is equal to 1/4 of X, which will be equal to RD. Why equal to RD? Because as we can see, 1 is still on AB. So if that is the case, therefore VB here will be equal to VB on the right portion, and there is no other loading rather than VB for RD to counter. So that is why at left of B, VB is always equal to RD. Okay, that's the point. So that is for left of B. So just right of B, RD will always be equal to 1. Why? Once your 1 here will abandon AB, there will be no value for RA as well as shear at B. Okay? So therefore, shear at B has no value. So only 1 will left. Okay? So the 1 here will be applied. Therefore, VB here will be equal to 0 now once this 1 will transfer to this. Therefore, RD will always be equal to 1 when your unit load 1 will be on the boundary of B to C. That is why we can see here that the ILD for the reaction at D, so when X is equal to 0, your RA is equal to 1. Okay? When your RA will be equal to 1, or here, shear at B is equal to 1/4 of 0, that is 0. Okay? And then when X is equal to 4, your VB is equal to 4 over 4, or that is equal to 1, which will be equal to RD also. So this is 1. Okay? And again, just right of B, your RD would be always equal to 0. So that is why consistently it is 1 here. Okay, so that is for ILD for RD. So let us put a check mark on this 2. So now we are going to proceed with moment 3 meters from A and shear 3 meters from A. So we will be using the same figure. Okay, so where's that? 3 meters from A. So 3 meters from A, we need to cut a section that is B prime. So if this is the cut portion, so we'll be having here a V prime. And also, we have here moment at B prime. So by employing the rule that summation forces vertical is equal to V prime, okay? So when we have a distance that is just left of B prime, we will include 1 here, okay? So 1 is still on the beam, just left of B prime. So therefore, that is going upwards RA, that is positive. We deduct the unit load 1. So this is an equation for X is 3 minus. And this is an equation for X is 3 plus. So for VP prime, for this segment wherein 1 is no longer present on the beam, we just remove 1 here, okay? We'll just remove 1 there. That is why VP prime for that condition is always equal to RE. Now if we are going to consider VB prime, we are going to have this tabulation. So when X is 0, VB prime, by the way, VB prime is actually related to RA, okay? So we have already established the equation for RA. So where shall we get the equation? Actually, we have already determined the ILD for RA. So here it is. However, what is lacking here is we do not know this particular value. So we need to get this value, wherein this is 3 meters. Because we are concerned with moment at 3 meters from A and shear 3 meters from A. So this is A. So we measure 3 meters. We need to get the value of RA at X is equal to 3 meters. We have two methods here. First, we can use by ratio and proportion of the triangle. We can say that 1 is to 4. So if I'm going to delegate that as Y is equal to Y is to 1, right? So this is 1. So therefore, Y at that point is equal to 1/4 or equal to 0.25. So if we are going to use the similar triangles. But if we intend to use the equation, okay, so here is the equation just left of B. When X is equal to 3, 1 minus 1/4 of 3. So 3/4. So this will become 3/4, right? So 3/4 is 0.75. Okay, so 1 minus 0.75, that is equal to 0.25. So we need that one in order to determine your VB. So as we can see now, we have this one and 3 x at x is equal to 3, RA is 0.25. And at x is equal to 4, your RA is equal to 0. So where's that? When x is equal to 4, your RA is equal to 0. So we tabulate your shear at B prime when x is 0. Okay, when x is 0, we use this. RA is 1, right? So 1 minus 1 is 0. Okay, at left of 3, just left of 3, or left of B prime, actually, we have an RA equal to 0.25. So RA is 0.25. And we're gonna use this equation. Okay, so 0.25 minus 1 is negative 0.75. So this is the value. And then 3 plus. So if we have a 3 plus, then RA, we use this. VB prime is always equal to RA. And your value at 3, value of RA is 0.25. So we'll just copy this. So we have this value, 0.25. So just right of B, RA is 0. So as we can see in the ILD, from B began to have a value equal to 0. So by that, just right of B, RA will be equal to 0. Always equal to 0. And an equation from 3 plus, your VB prime is always equal to RA. So if RA is 0 consistently at that portion, so therefore, your VB prime is equal to 0. Okay, so that is for our tabulated values. So if we are going to graph or plot that one, so this is ILD for VB prime. Okay, so it started from 0, and then just left of 3, we have negative 0.75. Okay, this one. And then just right of 3, we have positive 0.25. And then it will yield to 0 from there on. Okay, up to that point. So this will be our ILD for VB prime. Okay, next, for moment at B prime, again we will cut the portion 3 meters from A, and then begin to write the equation. So remember that MB, that the moment equation is just that one, summation moments. Summation moments, just stick to this ruling. This is positive and negative. So as we can see, MB prime is equal to 3 times RA. So just take moments at this point. That is a positive 3 RA minus, so this one. So 1 is still on the beam. Okay. So we will have this distance. What is this distance equal to? So if this is 3, this is 3 minus x. And this tends to bend your fiber concaving downwards, so that is negative, times the moment arm 3 minus x. So we'll have this equation for MB prime. And then just right of B, 1 will no longer be on the beam, so we'll just remove this portion. So MB prime will be equal to 3 RA. Okay. And then we have already plotted this actually, that when x is equal to 3, RA is equal to 0.25. And then your MB prime, you'll just have to use this one, 3 times RA, 3 times 0.25 minus 1. Okay. 3 minus 3. So 3 when x is equal to 3. So this becomes 0. 3 times 0.25 is actually 0.75. And then just right of B, MB prime will always be equal to 3 RA. Okay? And what is the value for RA at that portion? 0. Sorry. Your RA is always equal to 0.25. That is why your MB prime will be equal to 0.75. So if we notice, just left and right of B, we have yielded to a similar value. So it will start with a 0 value. So why 0 value? Because MB prime, using this equation, x is equal to 0. So this will yield to 0. And then RA is 0 at that point. So that is why MB prime started with x is equal to 0, and then just left of B prime, it is 0.75 and 0.75 as well for just right of B. And then you'll yield back to 0. Because when x is equal to 4, by the way, this distance here is 3 and this is 1. So this is actually 4 meters. And then when we reach 4 meters, when x is equal to 4, r is always equal to 0. So we can see that in our ILD. So in your ILD, your RA stays at 0 from x is equal to 4. Okay? Sorry, this should be in feet. So this distance should be. So anyway, x is equal to 4, r is equal to 0, MB prime is using this equation. Just right of B prime. MB prime is 3 times your RA. And your RA will always be equal to 0 once it reached 4. That is why MB prime is 0. So and it stays at 0 from there on. So this will be our influence line diagram for the moment at B prime. Okay. Okay, so moving on to this problem. We have here a frame, but your loading is still on a vertical. Okay. So this is similar to a beam. Okay, so this is just similar to a beam that is supported by roller. So this is a roller. Just transfer the pin connection here, and there will be an overhang here. So this is A, B, C, and D. Because Vertical here has nothing to do with the vertical loading that is transferring from one point to another. It can only have a effect if your loading is horizontal. Okay, horizontal. So anyway, it is quite similar to this one. So I have already illustrated the ILD for those requirement here. So we'll just have to expound our solution here. For RE, first, we will be having a illustration. Say we have here 1 is the unit load measured x from A. So we are concerned with RE. Basically, we are going to take moments at C. So you'll be having a distinct equations for x is equal to let us indicate the distances here. So this is 2, this is 3, and this is 2. So an equation for x that is less than 5, okay, or 5 minus. So let us indicate that by 5 minus. So writing the equation, summation moments at C is equal to 0. We have negative 1. What is the moment arm? 5 minus x. 5 minus x, and then plus 5 RE, and this will be equal to 0. So we maintain RE and then transpose this to the other side, becomes 5 less x. So therefore, RE will be equal to 1 minus x all over 5. So this is an equation for x is equal to 5 minus. And then for x which is above 5, we utilize the same equilibrium equation. So we take moments at C. This time, your x will now be on this portion. Sorry, your 1 will now be within that portion. So this is our x now. Okay. This is the unit load 1. So taking moments at C, we have to consider this distance. And what is this distance? X minus 5. X minus 5. And the rotation of that unit load is clockwise. So we have 1 times the moment arm, and then another clockwise 5 RA is equal to 0. So therefore, RA will be equal to x. Sorry. This now becomes negative. Negative x all over 5. This becomes positive. 5 over 5. that is 1. Negative x over 5 plus 1. So we have two distinct equations for a transferring load or unit load. Just left of C and just right of C. So we tabulate. Say x against its RE. So when x is equal to 0, we use this equation. Therefore, x RE is equal to 1. And then when x is equal to 5 minus or less than 5, so simply substitute 5 here. 1 minus 5 over 5, that is also that will be equal to 0. And then when x is equal to 5 plus, we use this equation. Negative 5 over 5 plus 1, that is also equal to 0. Now, if x is 2 plus 3 and 7, when x is equal to 7, we use this. So, negative 7 divided by 5 plus 1, that is equal to 0.4. Okay, so plotting that one, we will have this ILA for reaction at A. Okay, so next, we are now concerned with RE. So this time, of course, still use this figure. So using this figure this time, we are now concerned with the RC. So reaction at C. Sorry, this should be reaction at C. So anyway, doesn't matter RC or RE, because as I have said, that is similar. So perhaps you can just denote that by RE, since we have this column here. So this time we have summation moments at A. It's equal to 0. So having that one, we have clockwise 1 by x, another clockwise, minus 5 RE is equal to 0. So therefore, RE is equal to x 12 over 5. So this is an equation for x 5 minus, and another equation for x 5 plus. We have summation moments at 8. So this time we are going to consider this one here. Okay, we have 1 by x minus 5 RE. So anyway, we have yielded to the same equation all throughout the beam. So just plot this one, see x against its reaction at E. So when x is equal to 0, R is equal to 0. And then when x is, what is next to 0? 0 and then 5. So if you want, we stop at 2. When x is 2, that is 2/5 equal to 0.4. And then when x is equal to 5, that is equal to 1, 5 over 5. And then when x is 7, 7 over 5 is 1.4. So if we are going to plot that one, we have this. X is equal to 5, 1, and the 7 is 1.4. So somewhere in 2 meters. Say this is the 2 meters. We have a value of 0.4. Okay, so this is the ILE4 reaction at E. So moving on to shear at B and moment at B. We'll just have to use this one, okay, considering the left portion. So on the left portion, we can see that if we have this beam, there will be RA in it, okay? So B is 2 meters, or A to B is 2 meters. So this is a scenario wherein X is 2 minus, wherein your loading still within the beam. So this is B. This is the unit load. So this is our X. There will be VB and moment B at that point, and first we just copy this. Okay, and then make this as 2 plus, and if that is 2 plus, then you can already remove this, meaning one abandoned this segment. It's already on this outer segment. Okay, so if we have that one, we just have to write the shear and moment equations. Say we have VB simply equal to summation forces vertical. So VB is going upwards RA, that is positive, minus 1. So the unit load still there. So we reflect that one. So the moment at B is equal to positive RE, and what will be the distance from this one? that is times 2. Okay. RA times 2. And then for this, uh, anyway, let us deduct here the effect of 1 because 1 is still there. So minus 1 times 2 minus x. Say this is 2. That is 2. So therefore, our moment at B is 2RA minus 2 plus x. And then for this, VB, we'll just have to remove 1 because 1 is no longer here. MB is just equal to 2 times RE. So if we need to tabulate that one, perhaps we can utilize our tabulation a while ago. It was erased already. Anyway, we'll just refer to the ILA here. So what do we need? We need the value at 2 meters for RE. So here's the 2 meters. Perhaps we can use ratio and proportion. See, this is why we can say that 1 is to 5. Say this is 5. This base is 5. The bigger triangle versus the smaller triangle. So this is 3 meters. So we can say that this is y is to 3. Therefore, y is equal to 3 all over 5. And that is equal to 0.6. So if we intend to tabulate that one in our equation a while ago, we'll just come up with the same. So when x is 2, your y will be, your RA is 0.6. Why 2? Because we are concerned with the shear and moment at B. Okay. So we can now tabulate when x is 0. Your RA a while ago is 1. When x is equal to 2, here it is, 0.6. And then when x is 5, 0. We have a 0 value there. And then after 5, we have this one, 2. X is equal to 7. So what is the value of our R? 0.4. Then we can add on here the value for VB and MB. So when x is equal to 0, VB is RA minus 1. So 1 minus 1 is 0. And MB 0, this is 0, that is 0, so we have negative 0. So we check 2 times 1, 2 minus 2, 0, plus x is equal to 0, so 0. And then shear at B, so we'll have a B. Perhaps we can reflect here more detailed one. Let us just move this one. So that we can have here 2 minus and 2 plus. So just the same, we'll have the same RE. And then shear at B at 2 minus. So here it is, 2 minus. We'll use this equation. RA is 0.6. 0.6 minus 1 is actually negative 0.4. And 2 plus VB is equal to RA. And RA at this 2 plus is 0.6. So we have 0.6. And then for each moment, 2 negative. So we use this equation here. 2 times RE, 2 times 0.6, that is 1.2, minus 2, that is negative 0.8, plus 2. So let us write 2 times 0.6 minus 2 plus 2. So this is just cancelled. So 0.6 times 2 is equal to 1.2. And then for 2 plus 2 times RE, we use this one. And RA at this point is 0.6. 2 times 0.6 is also 1.2. And then for x is equal to 5, so we're going to use x is equal to 5 already exceeded 2. So therefore, we'll just use this equation. So your shear at B is equal to RA, and that is equal to 0. And your moment at B is equal to 2RA. 2 times 0 is 0. And VB is equal to RE. We just copy this, 0.4. And 2 times RE, our MB, that is equal to 0.2. So if we take a look at this plot, here it is, ILD for VB. At x is equal to 0, 0. Just left of B, 0.4 or negative 0.4. Just right of it, positive 0.6. Okay, this is negative. Okay. And then x is equal to 5, our shear is 0, so here it is. And x is equal to 7, our value is 0.4, so here it is. And ILD for MB, you can see here, started at 0. Okay, so 2 minus and 2 plus is both 1.2. X is equal to 5, 0. And x is equal to 7, 0.8. So this is actually the solutions for your previous quiz last time. So I'm gonna show you a better or simpler way how to determine these um, diagrams in just a couple of perhaps minutes or seconds. You can do it. Okay, so stand by for that procedure. So thank you for listening.